Hello and welcome you all for Unit 3 of Mass Transfer Operations. In this video lecture, we will be learning on distillation, that is part 3 design concepts. In this particular video lecture, I'll be discussing with the method called as McCabe Thiele method, using which we can design theoretically the number of equilibrium stages. Now just have a closer look at the distillation column. You can think of two different types, that is tray tower and packed tower, which are commonly used for continuous distillation operation. In tray tower, whether it is tray tower or packet tower, you have liquid and vapor which are moving in a countercurrent direction, and they establish the vapor liquid equilibrium. Usually the feed is fed at a particular location, whether it is tray tower or a packet tower. The explanation remains almost similar. The feed is entering somewhere in the middle, and it has got a particular temperature. The liquid could the feed could be subcooled at its bubble point, or at its dew point, or it could be superheated. Based on that, a quality parameter is measured, having how much amount of liquid is present in that enters the tower. It flows downward or upward based on whether it's liquid or vapor. At the reboiler point, it heats up and goes up, and on the top you have a condenser. The vapors are entering into the condenser, then it is condensed back into a liquid form. The liquid, whatever it is condensed over there could be a partial condenser or a total condenser. Total condenser is the one which completely condenses vapor into liquid form. Partial condenser is the one where liquid vapor or vapor liquid equilibrium coexist. Some portion of the vapor is uncondensed, it coexists. Now the condensed liquid what you have, it could be sent back to the tower in the form of liquid, that's called as reflux. A portion of the product, the condensed vapor liquid, it can be sent back to the tower as a reflux, and some portion is taken out as the product, L and D. That ratio of L divided by D, that is how much liquid is sent back, moles of the liquid sent back to the tower, and how much of the product is taken out. L by D is called as reflux ratio R. Then you have a condition called as total reflux and minimum reflux. Total reflux is the case when you do not take any product out. The entire condensed liquid is sent back to the tower L completely. Means D is 0. That condition is called as total reflux. Minimum reflux is the condition. It's not L0. Reflux is there, but minimum possible value of L is given. Below that, the tower may not be able to operate. So some amount of liquid is given, but that's the lowest amount of liquid that is given out. Obviously, D becomes maximum. So maximum amount of product is taken out. Now the reboiler, what you have here, that heats up the liquid that is coming down to the column, and it issues vapor and it is sending back to the tower. A fraction of that is taken in the bottom liquid product. We denote it as B, F, B and D. The reboiler generally has got one equilibrium stage. Then comes the number of equilibrium stages, which is a point of interest over here. From the top we generally count. From above the feed section, the number of equilibrium stages what you have, that's called as the rectification section. Below the feed stage, the number of stages you have, equilibrium stages or the trays you have, is called as stripping section. In the case of tray tower, we call it as a tray. In the case of packet column, we call it as HETP, height equivalent to theoretical plate. So that because each of them has got one equilibrium stage, denoted as one stage. One equilibrium stage is nothing but we assume that equilibrium between liquid and vapor takes place, whereas that's theoretical. That is why we calculate all theoretical considerations here. In reality, there may not be required amount of equilibrium condition maintained, so it may be a little far away from the equilibrium condition. That's why all the calculation what we do here is a theoretical prediction or the calculation. Let's have a little detailed insight on the rectification, that is enrichment. It's also called as enrichment or also known as rectification. It's that part of the fractionation column or the process in which concentration of the more volatile component is increased in the upper section of the fractionation column. So in the fractionation column upper section, the concentration of the more volatile component in the vapor is increased in this case. Whereas in the stripping section, the part of the fractionation column in which more volatile components are stripped from the liquid phase in the lower section of the fractionation column. So in the stripping section, more volatile component is removed. In the enrichment section, more volatile component is required. It is the same thing. But in stripping section, what we do is from the liquid stream where a large quantity of less volatile component is there, from that the more volatile component is removed. That means we require more volatile component more in the vapor phase, remember. So that is done in the stripping section. Whereas in the enrichment section, the vapor concentration is very large in the liquid as well as vapor. From the liquid phase, the more volatile component is removed. That is the enrichment. When you design a fractionation column, there are two main aspects. One is process design, second one is mechanical design. Let us concentrate mainly on the process design concept, where you come across material balance equations, you calculate number of stages, theoretical stages required, even practical stages based on stage efficiency. Mechanical design includes the tower height, diameter, and other mechanical aspects of the tower, whereas process design thinks about the process flow parameters and theoretical, that is the equilibrium stages in detail. The calculation of stages can be done by different methods, graphical as well as algebraic methods. Lewis Sorel method is one such method, which is base for McCabe Thiele method. McCabe Thiele method is the graphical solution for calculating the number of stages, which we are going to look into in detail in the next coming up slides. Poncon-Savret method is another equivalent method, which is also quite commonly used. So here we'll be looking into McCabe Thiele graphical method. It helps us to determine theoretical equilibrium stages. You see a graph here and a tower. A tower has got stages, feed line, stages, right? So equivalently, based on the XY, that is equilibrium diagram, vapor concentration and liquid concentration for the more volatile component, equilibrium diagram will be drawing. On this we'll be drawing certain lines. Many lines are there. Looks confusing, right? So let us see how it is done. We'll have to draw this particular diagram and calculate how many stages are there. So how this is done, let's look into this. All right, there are 6 different steps. So let us have look at one by one. Step 1, we establish the plot first. After that, we add the equilibrium data over and above that. In the third step, we add Q line, feed condition we add to the curve. Then we calculate operating line for the top section, that is enrichment rectification section. There are two sub-steps here. One, we calculate for the minimum condition, then we calculate for the actual condition, then we calculate in the step 5 we calculate the operating line for the stripping section, and in the last step we calculate the number of stages, how many stages are present. So let's look into it little detail, how these each steps are done. Let's look into detailed way. So what you can do is, we'll have a problem, we'll solve a problem. You read the problem, you can pause the video and read the problem. You can come back after you have completely read the problem. Alright, the problem will break it down into different components. Here there are information that are provided to us. Let's look into that in detail. So you have been given with the compositions XF, YD and XP. What are they? They are the molar composition. Remember, we require only molar composition here in the entire analysis. No other compositions are allowed. Only molar analysis will do it. Molar composition of the feed, distillate and bottom product. XB is the bottom product. 6 mole percent that is given, 93 mole percent and 35 mole percent. So that is the mole fraction of more volatile component. There are two components given here, component A and component B. So in this I'll say that component A is more volatile. I am identifying that component A is more volatile. How do I know it? Here there is an information. Relative volatility of component A to B is more than 1. That's 3.4. That means A is more volatile than B. This is clue number 1 for me. Clue number 2. Component A concentration in the distillate is 93%. So that is component A is very rich in the distillate product. That means more volatile component will go to the distillate, right? So component A must be the more volatile component. So let's write down the values. You observe that combination concentrations, bottom product concentration is the lowest, distillate concentration is the highest, feed comes in the middle. Some more information that we have here, let's highlight that. Feed is saturated with half vapor or otherwise half liquid. Just true, vapor and liquid, there are only two possibilities, right? Half vapor, half liquid. So feed is saturated with half liquid or half vapor. I don't know what it is. Let's look in the next slide. Okay, let's go to the next point. Reflux ratio is 1.5 times the minimum reflux. That's also a little coded, but still we'll write it down. Relative volatility, okay, alpha, that's known to us already. Alpha is equal to 3.4. So some more information, that's question that you need to address is minimum reflux ratio. How much is the minimum reflux ratio? How many equilibrium stages are there? And one information is given to us. Consider a total condenser and a reboiler in the operation. So these are the information that is available to us. With respect to this, let us solve the problem. Now, given the information, we have to tabulate all the information. So let us go one by one. Alpha is given to us, feed data is given to us, then there is a Q value coming into picture. What is this Q value? I told you earlier in the problem, there is one information, the feed is saturated with half vapor, half liquid. So half 50%, right? Saturated with 50%. For this case, Q is equal to 0.5. Once this problem is over, numerical is over, I'll give more detail onto Q, the different cases of Q, how you can identify the value of Q based on the condition. Another information that is available to is composition, that is a target composition. Y and X, XT and XB both values are given to us. You'll use the if that data is not available, you can use the material balance equations, that is FD and F is equal to D plus B, and this component balance equation you can use. If one is known and other is unknown, based on the available data you can calculate. If the total quantity is not available, you can take a basis of 100 mole per hour or 100 kilomole per hour. 100 for the feed flow rate of 100 kilomole per hour, you can take it as the basis and you can calculate the rest. And basically we require three concentrations, XF, XD and XP. This you have to evaluate before you start analyzing the problem. Then you have to plot the graph. What is this plot? Right, so you will plot one XY diagram, x-axis, y-axis, that is y on the y-axis 0 to 1 with an increment of 0.1, 0 to 1 in the x-axis and with an increment of 0.1. Most important, it's a square graph, that means the scales are equal in both the axes. After that, draw x is equal to y line, diagonal line, starting from 0 0 up to 1 1. Draw the diagonal line, then mark the points. Which points? Three concentrations, XF, XD and XB. XB, XF and XD, I am marking it on the that is XY line. X is equal to X versus Y line, right? Now here I have taken XD because it's in the liquid phase. Remember, in the tower it is coming as a liquid, flowing down as a liquid, so I have taken it as XD here. Alright, next you have to generate the XY data. How do we generate XY data? So there are two possibilities. Given alpha of the binary system, that is alpha is given to you, you have an equation y is equal to alpha x by 1 plus alpha minus 1x. This is a ideal binary system relation of x versus x and y. Given the alpha, substitute the value of alpha, find out y versus x. That is, for values of x starting from 0 to 1 with an increment of 0.1, this you have to generate. This value you have to take it on your own. Take x is equal to 0 up to 1 with an increment of 0.1. Substitute each value in this equation and find out the y, and this is your x versus y data. Alternatively, if alpha is not there, that is alpha may not be given, directly this x versus y data is given to you. That's great, because you don't have to do the calculation. This data is directly available to you. That's possible. Alright, now you have the graph already. You will have to plot this on the graph what you have, right? The red line, right? The equilibrium data, this vertical value is plotted here, y versus x. This is step number 2. In step number 3, what we do is we add the q line feed condition, we add to the graph. Now for doing that, we need some information, because you have to draw a line. You need some information about the line. What information? This is the q line equation. Just think about it. How does it look like? Q and xf are the constant. So q by q minus 1 is a number. Xf minus xf by q minus 1 is a number. So it is y and x are the variables what we have plotted on the graph. Y versus, or y is equal to mx plus c. So slope m is equal to q by q minus 1, and intercept is minus xf by q minus 1. This is the intercept. It's a straight line. Y is equal to mx plus c form. In this equation, q is known to us, xf is known to us, so easily we can calculate y-intercept and slope. So the y-intercept is 0.7, slope is minus 0.5. Next, what we have to do is we have to draw one line on this graph representing this information on this graph. This is the previous step outcome. So to draw this, what do we have? We have y-intercept 0.7, we have one slope minus 0.5. Fine, no problem, but we can draw the line. But it is easy if you have 2 points, right? If you have 2 points, just connect them, you get a line. Fine, let's look at this equation again. What if this x, this is a variable x, what if this ex is equal to xf? If I put x is equal to xf, what will happen? Take a pen and paper, check it out yourself, substitute x is equal to xf, simplify the right hand side. You'll wonder that y is equal to xf is your answer. That means this particular line passes through a point xf comma xf, or this particular line here. So there are 2 points. This particular point is xf comma xf, 0.35, 0.35. That's on the diagonal line, x is equal to y line. So the line q line passes through this particular point xf comma xf. So on the diagonal line, identify xf. That's the point number 1. Point number 2 is your intercept. Connect them. Don't draw the line up to the end, draw the line only up to the equilibrium point. This solid line is called as q line. So in the step number 3, you have drawn the q line. Right, in the step number 4, we are going to draw the operating line for the rectification section. For the rectification section, it's a straight line. This is the operating line equation. Y is equal to slope into x plus intercept. Again, we know it already. We are a bit familiar to this kind of drawing the equations. That is, given the slope and intercept, you can draw the line. Given the 2 points, you can draw the line, right? So r by r plus 1. But this r is not known to us. R is given in the form of r is equal to 1.5 times the rm. Rm is the minimum reflux, which is not known to us. We have to calculate that minimum reflux. Then coming over here, intercept xd is known to us, but again the r is unknown to us. So if you have to draw r, you have to calculate rm. So let us analyze what it is. So this is the outcome of previous step. Step number 3, we have got this curve. Now operating line is given to us at minimum reflux ratio. Rectification operating line ROL, it passes through something called as pinch point. This is important. Minimum reflux condition only this happens. Operating line passes through a point called as pinch point. So this pinch point is one point for us. Another one, you do it yourself. Take a pen and paper, put x is equal to xd, distillate concentration, product concentration, xd, put it xd, simplify the right hand side. You'll wonder to see that y is equal to xd. That means it passes through a point of intersection of xd and diagonal line. That is here, this xd and this somewhere here on the diagonal line where xd is coming. At that point it passes through which one? The operating line the rectification section, irrespective whether it is minimum or any other condition, right? So that is one point. Another point is pinch point. So let's see what is that. Yeah, this is XD on the diagonal line, point number 1. Point number 2, this one is called as pinch point. What is this pinch point? It is the intersection point of Q line and the equilibrium line. Equilibrium line and the Q line intersect at a point, and that point is called as pinch point. So draw the line. Just connect this point and this point. After that, you extend this line to the y-axis. Why should I extend? Y-axis, when I extend it, I get the intercept. So this is the intercept. Intercept is 0.349. Remember, this is the rectification operating line for the minimum reflux condition. So for R is equal to Rm, the intercept, this one, this intercept is equal to, for the minimum reflux condition, Hd by Rm plus 1, which is 0.349. So Hd is known to us, 0.93. You can calculate Rm. Rm is equal to 1.667. So now we know how we draw the minimum reflux operating line pinch at the pinch point. Then we extend it, we get the intercept. Using intercept, we calculate minimum reflux ratio. Given the minimum reflux ratio, you can calculate the actual reflux ratio. What is that reflux ratio? 1.5 times minimum reflux ratio, which comes out to be 2.5. Alright, so we know the R value now. We have the operating line equation as earlier. That is, it passes through XD or diagonal line XD, and another one is intercept XD by R plus 1. That information we have. So we can calculate that y-intercept, XD divided by R plus 1. XD divided by R plus 1. Now R is 2.5. So you calculate and it comes out to be 0.266. So let us draw that. So point number 1 is intersection of XD and the diagonal line. XD and the diagonal line, same point as minimum reflux. New operating line, actual operating line will be drawing now, but not by some point. One point is this, second point is this intercept, which you have just calculated by XD by R plus 1 equation. This one, XD by R plus 1, which is 0.266. So here it is 0.266. Using this point, point number 2 and point number 1, connect them, and you see that it is connecting the Q line somewhere in between the diagonal line and the pinch point. In between the pinch point and diagonal intersection, somewhere in between it comes, or it intersects. Which one? Q line and rectification operating line. So this is your dark blue line. This one is the operating line for the rectification section. That's the end of step 4. Alright, step 5. What we have to do is we have to draw the operating line for the stripping section. That's very easy. You identify the intersection of operating line of rectification section and Q line. Operating line of rectification section and Q line intersection. Here is the point. One is this. Second one, intersection of diagonal line and XB. Diagonal line and XB. Here it is. So you connect the 2 points. Pink line. One point is this, second point is this. This is XB. So connect this diagonal, this particular point on the diagonal line, XB, and intersection of operating line of rectification section and Q line, this particular point. Connect them. That's the operating line for stripping section. It's a straight line. Stripping section, operating line. That's a step 5. In the step 6, you will calculate the equilibrium stages. So how will you do it? You will, this is already drawn. You'll start calculating. You'll start from this point, the diagonal line, this particular point XD on the diagonal line. You'll start. What you have to do? You have to start from there, continue up to equilibrium line. You continue up to equilibrium line. Once you reach the equilibrium line, drop the line to operating line. Operating line, which one? This particular line, dark blue. That is the rectification section operating line. So you just have to continue, and use the top line till you cross the Q line. Till you cross the Q line, you have to draw the step down line like this. Once you cross the Q line, you have to use the operating line for stripping section. This particular line you have to use it. In the end, you have to continue the same mechanism. So let me highlight this particular area for you. Alright, the blue line is the operating line for the rectification section. Pink line is the stripping section operating line. Purple color line, this line is the Q line. Red line is equilibrium line. So from the equilibrium line to the ROL, equilibrium line, ROL. Now it has crossed the Q line. Remember, it has crossed the Q line here. At this point Q line is crossed, reaching the equilibrium line. Now it has to come to the stripping section operating line here. It has to touch this one once it has crossed Q line. That's very important. Be careful at this particular point. Right, what next? You have to continue the procedure till XB is crossed. That is, till you cross this XB, you will have to continue. So let me zoom that particular part. This is the stripping section operating line, equilibrium line. It is connecting here. Yes, you have crossed the XB. You will have to stop. This is the end point. Here you have to stop. This is the end point. Right? This particular point is not counted till end. This is the end. Alright, continue the procedure till XB is crossed. Count the number of times this line touches equilibrium curve between XD and XB. XD and XB. This line XB and XD. Between that, how many times this line and this particular crisscross line touches equilibrium line? Count it. 1, 2, 3, 4, 5, 6, 7. So totally 7 times it touches the equilibrium line. Remember, it is beyond XB. It's after XB, not counted now. Then the number of stages is equal to how many times it touches the graph. That's how you calculate. So number of stages is equal to 7. Now let us do some more analysis, detailed analysis. How many trays or stages needed now? We are given that condenser is a total condenser type which takes equilibrium stage 0. There is no equilibrium available in the condenser. Whereas reboiler, there exists one equilibrium which is at the bottom. Reboiler is below the stripping section. Remember, condenser is above the distillation rectification section at the top. So the last one, 7th stage, is nothing but reboiler. So we will be deducting 1 for that. So the number of theoretical stages, a number of trays required is total minus how many stages required for reboiler minus how many stages required for condenser. That is total is 7 minus 1 minus 0. That gives you 6. So 6 stages are available. Let's look at that little detail. Feed stage is at the 5th stage. Feed is given at the 5th stage. How do I know that it is at the 5th stage? Count the triangle. Consider this particular triangle. This triangle below 1 is the tray number 1, tray number 2, tray number 3, tray number 4, similarly tray number 5. The Q line encroaches or passes the triangle number 5. This triangle in that Q line is passed. Through this particular triangle, Q line is passed. That is why your feed is entering in the 5th stage. The stages above the feed stage is exclusive, keep it separate. Above this, stage number 1, 2, 3, 4 are the top section, that is enrichment section. There are 4 stages. Below the feed stage, exclude this. Below the feed stage, stage number 6 is the bottom section or stripping section. Don't forget, 7 is the reboiler, 7th is the reboiler. This is reboiler, stripping section 1 stage, feed stage 1 stage, 4 top enrichment section. So that's how you solve the problem. We have come to the end of that particular problem. Now we have to address certain issues, some questions. That is, what is quality of feed? Right? We have taken Q is equal to 0.5 in the problem. What is that? How do we analyze it? So the Q is the condition of the feed stream F entering the tower. Feed stream enters the tower now. It determines the relationship between molar flow rate of vapor and liquid stream. How much vapor, how much liquid in the feed in enriching and stripping section. That means when you provide the feed to the allow the feed to enter the tower, there may be some amount of liquid, there may be some amount of vapor, or only liquid, only vapor. Multiple condition possibilities are there. Based on that, it will move inside the tower. If it is liquid, it will go down because of gravity. It goes to the stripping section. If it is vapor, it moves up to the enriching section because of lighter density, right? So how much amount of liquid is present, that matters. So there are different possible conditions of feed quality based on temperature. Why temperature? Because temperature is the one which determines whether the stream contains the amount of liquid or vapor or anything. So in simple, feed quality you can define it as what fraction of the feed is liquid, how much liquid is present in it. So this is how it is defined. Heat needed to vaporize 1 mole of feed at entering the condition divided by molar latent heat of vaporization. So if you have to heat the entire thing, it is a molar latent heat of vaporization. This is a theoretical condition. This is the actual how much you have to require. So we'll get to know whether it is liquid stage, some amount of liquid stage, or completely vapor. So this is the Q line equation which we have already used. Q by Q minus 1 is the slope that we have to concentrate. Q by Q minus 1 is the slope of the Q line. Now based on that particular condition, that is quality, we have different conditions here. Cold feed is completely cold. Feed is at its boiling point or bubble point, you can say. It's partly vapor, saturated vapor, that is at the dew point, and superheated vapor. Based on that, you will define the value of Q. This is how it is represented in the equilibrium line. This is the equilibrium line, this is the diagonal line, this is the point of intersection of Q and the diagonal line. For xf is equal to 0.5, this is strong. Different cases. In this region, it is Q greater than 1, this is at Q is equal to 1. From here, within this, Q0 to 1, that is 1 to 0 I can say, and below this Q is less than 0 here, superheated. Now the value of Q. So slope is calculated by Q minus 1. For example, if Q is equal to 1, 1 divided by 0, that's infinity. So it's a vertical line. If Q is equal to 0, 0 divided by minus 1 is 0. So slope is 0, horizontal line. Equivalently, you get different slopes. If both are equal, liquid and vapor both are equal, you will get 0.5. This particular line, somewhere in between for other conditions. Now it is easy for me to explain you with the boiling point diagram. This is the boiling point diagram which we have used earlier, right? So let me consider 50% mole fraction, 0.5 mole fraction of the feed. Say that this at point A is at this particular temperature, which is a subcooled region. The liquid is cold, subcooled region. Here it is subcooled region. For this, Q will be greater than 1. If you increase the temperature, that is to the bubble point, point B. At bubble point, that's called a saturated liquid. At this point, Q is equal to 1. Let me jump a little bit. That is point D, that is dew point. All the feed is vapor. That is called as saturated vapor. Saturated vapor. Here, point D. For that, Q is equal to 0. Just vapor. They are just vaporized, completely vaporized, just. In between this is the equilibrium, that is some fraction of vapor and liquid coexist. Here vapor is 0, completely liquid, so that is why Q is equal to 1. Here it is liquid is 0, it is completely vapor, so that is why Q is equal to 0. So in between you have different condition. As you move up, as the vapor increases, otherwise liquid decreases, Q goes on decreasing. So Q is proportional to the liquid quantity in this particular vapor liquid equilibrium. For example, if feed contains 75% of the liquid, somewhere here 75% of the liquid and 25% of vapor, Q is equal to 0.75. 75% liquid, Q is equal to 0.75. If the liquid is 25%, Q is equal to 0.25. If you remember previous problem, we had 50% vapor. That means 50% vapor, 50% liquid, saturated with the 50% vapor. Means 50% liquid, 50% vapor we have taken Q is equal to 0.5. That's how the quality of feed is measured. Alright, what we'll do is we'll solve the previous problem for two different conditions. So the first condition will take Q is equal to 1. Same problem, same data, except that feed is saturated, liquid. Q is equal to 1. What will happen? Let us see this. Slope is infinity. This is the line, Q line. So you can calculate Rm, then you calculate R using the same 6-step method. You calculate Rm as 0.954, R is equal to 1.432, and you find that number of stages is equal to 8. Previous problem we got 7 stages, here we get 8 stages. Same procedure you follow it with Q is equal to 1. Similarly, you can redo that problem with the Q is equal to 0, where feed is saturated vapor. Same problem, but Q is equal to 0. Now you see that slope of the Q line is 0. That's a horizontal line. Use that 6-step method. You find that Rm is equal to 2.72, or R reflux ratio is 4.08. For this, the number of stages required is 6. So you observe that as you change the value of Q, that is the quality of feed you change it, as you increase the heat, the number of stages also change. That's an important observation that you need to make. With the Q, change in Q, the steps also or the number of stages required also change. Okay, the next question comes, how does the reflux ratio affect the number of stage? Reflux ratio is nothing but L by D. So we have an operating line equation rectification section where R comes into picture. Slope is equal to R by R plus 1, intercept is equal to XD by R plus 1. For the previous problem where we have taken, first problem we have taken, XD is equal to 0.93, Q is equal to 0.5. For this particular case we have solved the problem, right? When you say reflux ratio, there are three different conditions you can think of. One is called as minimum reflux, one extreme end of the reflux, another condition called as total reflux, another extreme end, it's the complete reflux you are giving. In between these two you have the optimum reflux. Reflux ratio we define it as L by D. The reflux that is given as the liquid stream back to the tower divided by the distillate that you take out. Now, what are the extreme conditions? D. Minimum possible product that you can take out is 0. That means there is no product at all. If there is no product at all, if D is equal to 0, what will happen to R? L by 0, infinity. So, total reflux means infinite reflux condition. Under total reflux condition, reflux ratio is infinite, very large. Instead of saying infinite, I'll say very large. For this case, distillate is 0. This is one extreme end. On the other end, minimum reflux, D is maximum. You don't know the number, very large number. Let me say very large number. So when D is very large compared to L, this reflux ratio is minimum. This is a minimum possible value. It depends upon the pinch point what you have. Based on the equilibrium curve pinch point, you will get to know minimum value, minimum possible value. Below that it is not possible. So the optimal reflux ratio is 1.2 to 1.5 times the minimum, little above this, neither minimum nor maximum. We operate in between. That's called as optimal reflux ratio. There are certain issues associated with this as well as this. We'll see it at the end. Optimal ratio, we are going to use it. So operating line, rectification operating line for minimum reflux ratio, it touches the equilibrium line at pinch point. See here it touches the equilibrium line at the pinch point, sorry, Q line at pinch point. Whereas total reflux ratio, other extreme end, it coincides with the x is equal to y. The x is equal to y line, this x is equal to y line, it coincides with the two operating line for the top section, operating line for the bottom section. So for total reflux case is easiest way to solve. That if you just draw the equilibrium line, diagonal line, mark xt, mark xb, and continue with the crisscross step line and count the number of stages. And remember, this gives you the lowest required stages. Minimum required stages you can calculate using the total reflux condition. And for the minimum reflux condition, other extreme end, you get the large number of stages, almost infinity means very large number. For this particular case, 0.93 to 0.5, it's around 20 plus, and this is 4, and here we got 7 earlier for 1.5 reflux ratio, right? So this is how the reflux ratio affect the stages. At minimum reflux ratio, you have large number of stages. At lowest, at the total reflux condition, you have the lowest required number of stages. Now we don't use minimum reflux, we don't use total reflux in the operating procedures. We use somewhere optimal condition. The reason is that, let me assess with this. When you have zero distillate, zero product coming out of your tower, there is no use in operating in that or using that, because without product your commercial value of your process is zero. There is no use of that, right? So you need some product. So you cannot operate all the time with a total reflux. Yes, in the beginning of the process, to achieve higher concentration, to initiate the process, you may use total reflux. But over the time, once it attains a steady state, you'll go for uh, optimal reflux condition. Now, if it, that's how. And also you require, since there is no product, you will have, if at all you try to operate with this condition, your operating cost as well as total cost will increase. Very large total cost you will have. Whereas minimum reflux ratio, if you take it, you require large number of stages, the tower height may increase, you have fixed cost very high for this. Or in other words, maintenance cost and operating cost also very high for this. So accumulating a very high total cost in this case as well as this case. In between case, that is this optimal case, the cost of operating, cost of installation, cost of maintenance, that's the total cost, will be minimal compared to these two cases. That is why we use optimal reflux condition in the operations. Alright, I have some questions, so we'll try to answer that. Is it possible that n is equal to 3.3? Number of stages is something like 3.3. What is that 3.3? It's not an integer, it's a decimal value. Can be a decimal value. Theoretically, yes. When you solve a problem, you come across 3.3, 3.5, something like that. But in reality, think of this. You have a tray. You cannot have a fraction tray. You have a fixed one single tray, 2 or 3 like that. So it should be an integer. So practically when you consider it's an integer, theoretically you may come across the stage you can round it up to the next higher level. There are different methods called as optimal designs available. You can learn it on your own after once you have practiced this particular concept. How we use optimal designs for calculating the proper number of stages. Next question is, does the Q value impact total reflux condition? So Q value, feed quality, we have seen that it impacts the number of stages, but here the question is total reflux condition. Under total reflux condition, where two operating lines coincide with a diagonal line, that case, so whether the Q line has some impact. Under total reflux condition, Q value does not affect N. N is not affected. The number of stages remains same whether Q is 0, Q is 1, or Q is some in between 0 to 1 or any other value. But feed location, on which stage you provide the feed, it may change. Okay, here is another thing. I want to solve problem for practice. Where do I get it? Good. So you understood the method. Now you have seen that one problem or two problems solved here. Now I want to change certain thing. I want to practice on my own. Fine, that's great. Now for this, what you can do is you can refer any chemical engineering textbooks or any available internet materials where they would have provided you material related to the distillation process. You will get it. But there is one easier way you can do. What you can do is you can create your own problem for the practice. You just have to do this. The value that I mentioned there, you can make use of it. Use that 6-step procedure with this method. Any one value for each variable, you take it. That is the concentrations, bottom product, feed, and the top product. You take within this range. Any one value, take it. Any one value within this range, any one value within this range. Don't go beyond this range. It will be a little difficult to solve those cases. Very low concentration or very high concentration, if you take it, number of stages will be very difficult to do it manually. Alpha value, it should be more than 1 but not too close to 1. Something like 1.4, 1.5 would be sufficient enough, but don't go beyond 3.5, practically not possible. Then another is Q. Q you can go for like 1, 0, in between 1, 0. Extreme you can go by minus 2.5 plus 2.5. Practically okay. R, the reflux ratio is usually 1.2 to 1.6 times the minimum reflux. So you calculate the minimum reflux, to multiply it over 1.2 and 1.6, that your actual reflux ratio. Fine, you have another question. You have solved the problem, that's fine. The question arises now, how do I verify whether my solution is correct or not? You solved, you got a number of stage, you got the feed position, top section, bottom section, all those cases you got it. You solved it, whether it's right or wrong, you don't know how to verify it. Fine, I'll give you a solution for this also. Here is one website, the link is given in below this video. When you scroll down in that website, there is one link like this, download. When you click on that, Excel sheet will download. So open that Excel sheet, it looks like this, blue and pink color. In this blue section, the values what I mentioned in the previous question, so same numbers which you have used for solving your problem, substitute here. Feed you can put it as something 100, doesn't matter, it's a basis. Feed you can take it as 100 kilomole per hour, and rest whatever data you have used for your problem, substitute that here. You will get a graph, you will get number of stages here, number of plates is given, number of plates without boiler, that is without reboiler, the number given. So you have to add it to get the total number. This is one easiest way. I'll give you one more, that is interactive web page. Here alpha is fixed, you cannot have your own problem. This is for methanol water system, but it's an interactive. How does the reflux, all this condition change along with the interactive diagram, you can observe it. This is very cool, you can try it on. Both the links are given below this video, you can try it on your own. Alright, we have come to the end of the this particular lecture, summarizing what we have learned. So we have learned how to use the McCabe Thiele method to identify how we calculate, or how do we use the McCabe Thiele method to calculate number of equilibrium stages required for a process design of a continuous distillation system where reflux is present. Remember, reflux is very important. Without reflux you cannot use this method. So we found that first we established the data based on the available information. Then we calculate the equilibrium data. Otherwise, we are given with the equilibrium data, we'll put it on that. In step 3, we draw the Q line. We have also seen what are the different Q lines that are possible. Then we draw the rectification line that based on the intercept and pinch point. Then over and above that, we have actually calculated the operating line for the rectification section. Then we have drawn the stripping section. Then we have drawn the crisscross lines starting from XD up to XB. Also shown you how to use at this particular crossover point and identify the feed position, number of plates, number of stages above that, number of stages below that. Don't forget the one stage for the reboiler. Then we have seen the Q line, different Q lines, and we have seen how does it affect number of stages. Plus we have also observed how this Q value is calculated, and I have explained you using the boiling point diagram. And in the last part we have seen reflux ratio, two extreme conditions, minimum reflux, total reflux, then optimum condition, that's in between. How do we use it, what are the different aspects on this. Yeah, that's the end of this video. Thank you.